Hello everybody, in this video poster I will show you a possible way to chart the Ising universality class both in 2 and 3 dimensions. First of all, let me briefly recall the model on which all the discussion is based, which is the Ising model on a lattice. Here we will consider a square or a cubic lattice. We know that it is a spin model describing the interaction between nearest neighbor spins plus the interaction with an externally applied magnetic field. This model exhibits a critical behavior due to the Z2 spontaneous symmetry breaking, and if we perform a continuum limit close to the critical point, we end up with a quantum field theory, which is conformally invariant at the critical point and then perturbed along the 2 relevant directions corresponding to the energy and field and spin operators. In this setting, we want to study a universal combination of 2 thermodynamic quantities, the magnetic susceptibility and the correlation length. We define this combination omega, and it is defined by this expression. And it is particularly interesting because of 3 main aspects. First of all, because it involves observables that are rather easy to evaluate, both in numerical simulations and in experiments, because the magnetic susceptibility and the correlation length are linked to the order parameter of the phase transition, which is usually easy to identify. And moreover, we see from the definition of omega that they are normalized with respect to the amplitudes that they have along the line of first order phase transition, which is again usually easy to identify. Second, we see that this definition of omega depends on both temperature and the magnetic field, so it gives a description of the whole scaling region, while the usual universal amplitude ratios and the critical exponents are defined just at the critical point. And finally, since it is a universal quantity, our results will be valid not only for the Ising model, but for any physical realization of the Ising universality class. And in particular, we will concentrate on some examples in the context of high energy physics. So, having this in mind, we focus on this omega ratio that is defined in the whole scaling region. Here we know that the observables are described by a proper combination of temperature and magnetic field, giving a so-called scaling parameter, eta. So if we rewrite our function omega in terms of this scaling parameter, we end up with the fact that when only one perturbation is present, so when eta takes the values plus, minus, infinite and 0, the omega quantity can be rewritten as appropriate combinations of the universal amplitude ratios that we know are exactly known for the bidimensional Ising model, or they are given by numerical estimations for the 3-dimensional case. So in these 3 points, the omega quantity is already known, and our goal will be to extend these results to the whole eta plane, using these 3 values as benchmarks to test the reliability of our results. In order to address this problem, we study the parametric representation of the critical equation of state in terms of 2 parameters, r and theta, that basically describe the distance from the critical point. In terms of these parameters, we can rewrite the omega quantity, and we end up with this expression, where we see that only the theta dependence is present, Therefore, we conclude that theta plays the role of the scaling parameter that previously we called eta. And moreover, we notice that in this expression of omega, it is present the function h of theta, for which it is customary to use polynomial approximations. Therefore, depending on how good are these approximations for this function, we will end up with a good or not expression for omega. And in particular, in 3 dimensions, we used these polynomial approximations and we got these results for omega, here plotted with respect to theta and also eta. These results are really good because for the 3 points in the eta axis where only one perturbation is present, so plus, minus, infinite and 0, we get results in good agreement with the Monte Carlo estimations for the 3-dimensional Ising model. But not the same is true for the b-dimensional case. Therefore, we have to study this other case with another approach, and in particular, we exploit the fact that the b-dimensional Ising theory, when one of the 2 perturbations is 0, becomes an integrable theory. Therefore, lots of exact results are known, and also we can use perturbative expansions, for example, of the magnetic susceptibility and the correlation length around these axes of integrability. Doing so, we end up with these expansions for our function omega. And here we have the corresponding plot. Again, the 3 values at eta equal to plus, minus, infinite and 0 correspond to the exactly known values of omega when only one perturbation is present. So, in conclusion, we ask why should we be so interested in this function omega? The answer lies on the fact that there are many examples of Ising behavior in the finite temperature QCD, related in various ways to the confinement phase transition. For example, studying the Columbia plot, which is a well-known plot where it is depicted the nature of the phase transitions of QCD as a function of the quark masses, we can see that there are 2 regions of first-order phase transitions ending in lines of second-order phase transition that are thought to be of the Ising type. And moreover, the physical point corresponding to the physical values of the quark masses lies not so far from one of them. So a better study of the Ising universality class would help in the understanding of the physical point of the theory of strong interaction. But even more interesting is the case of the QCD phase diagram at finite temperature and finite baryonic chemical potential. In this regime, we know that Monte Carlo simulations fail due to the well-known sign problem. Therefore, all the study rely only on theoretical predictions and experimental results. In particular, from heavy-ion collision experiments, we know that there is a first-order phase transition line ending in a critical point, and it is believed that it is also of the Ising type. So again, a better investigation of the Ising critical region would help the understanding of this critical ending point. And so with this I finish. I thank you for your attention and I hope you liked the subject.